KLM has grounded 7 of its 24 Boeing 787 aircraft due to technical concerns involving a refueling component.
What did engineers uncover inside a KLM Boeing 787 that no one expected? And why could this hidden flaw shake the aviation world? From subtle vibrations to invisible structural weaknesses, every inspection revealed dangers the plane had been quietly carrying. Pilots, crew, and engineers were left questioning what had been trusted for years, as the discovery exposed a risk that could affect flights across the globe. Stay with us, because what they found inside this cutting-edge Dreamliner is really bad. The discovery nobody expected. The night shift at the Boeing facility was quiet, almost eerily so. Only the hum of ventilation and the soft beeps of monitoring equipment broke the silence. Technicians went about their usual rounds, checking sensors and logging readings, when one of them noticed a vibration that didn't match any expected pattern. At first, it was easy to dismiss. Machines occasionally gave false readings, and sensors could misbehave. But this anomaly had a rhythm, a subtle pulse that suggested something more. Deep inside the Dreamliner's fuselage, the sensors picked up micro-movements at a junction point that had never raised flags before. Engineers had designed these joints to flex slightly under stress, but the data suggested flexing beyond calculated tolerances. Curiosity turned into concern as the technician traced the readings along the plane's frame. Something was off. The irregularity was buried deep, far beyond where routine inspections could reach, and it seemed isolated, or so it appeared. Across the control room, experienced engineers leaned over the screens. They had seen anomalies before, but usually these were minor. This one, however, refused to behave like a minor glitch. Every test confirmed the same pattern. It was as if the aircraft itself was quietly signaling a hidden problem, an imperfection masked beneath layers of composites and alloys. No checklist, no maintenance log had prepared them for this. The Dreamliner, known for its advanced materials and futuristic design, had become a puzzle. Its lightweight composites and carbon fiber structures allowed for efficiency and performance, but also created areas that were difficult to monitor. Engineers realized that a flaw in one of these unseen spaces could exist for years without detection. The discovery challenged assumptions about the aircraft's resilience. Technicians began cross-referencing every piece of data from previous flights. The vibration, though subtle, matched no known flight signature. It was faint enough that passengers would never notice it, and even pilots would feel nothing unusual in the cockpit. Yet for those trained to read these signs, the signal could not be ignored. Every minute spent analyzing the anomaly made it clear that this was no ordinary maintenance finding. A sense of unease settled in the room. Conversations slowed. Heads shook slightly as teams exchanged glances. Could a small irregularity be the tip of a much larger problem? The implications were unsettling. Boeing's engineers were well aware of the intense scrutiny the 787 faced from airlines, regulators, and the flying public. Any hint of a defect, however minor, could trigger cascading concerns. The team decided to investigate further, using scanning technology usually reserved for deep structural checks. They examined stress points, bolt alignments, and hidden cavities within the fuselage. Each scan revealed more questions than answers. Some areas appeared untouched, pristine in their construction, while others displayed tiny irregularities that should have been impossible to miss. The deeper they went, the more complex the picture became. By the early hours of the morning, a pattern began to emerge. The anomaly wasn't random. It followed a path along a particular section of the aircraft, hinting at a structural weakness that had silently persisted. Engineers faced a stark realization. The problem had likely existed since assembly and had gone undetected through routine inspections, flight testing, and operational checks. This was the kind of discovery that could redefine maintenance protocols for the Dreamliner. As the sun began to rise, the team stepped back from their screens, exhausted but alert. They knew they were at the beginning of a deeper investigation. What had started as a routine inspection had turned into the first glimpse of a hidden danger that could ripple across the industry. The quiet hum of the facility suddenly felt louder, more ominous, as if the aircraft itself was holding its breath. Could one small vibration really uncover a threat buried deep inside one of the world's most advanced planes? Stay with us as the mystery deepens. The human stakes at 35,000 feet. While regulators and engineers debated behind closed doors, the reality of the hidden flaw began to ripple through the people who faced it in the air every day. Pilots, already accustomed to meticulously monitoring instruments and responding to unexpected variables, were suddenly confronted with the invisible risk of a structural anomaly. For many, the realization that an imperfection could exist without warning brought a deep sense of unease. Flight crews began to notice subtle patterns. Some pilots reported minute vibrations during specific maneuvers that previously seemed inconsequential. They described the feeling as a soft pulse, almost imperceptible, but consistent enough to prompt further attention. While these readings were well within operational safety limits, the connection to the anomaly discovered on the ground raised questions that had no immediate answers. The human perception of safety, trained over years of experience, was now at odds with a silent technical threat. Cabin crew faced their own challenges. Passengers rarely notice small changes in vibration, yet trained flight attendants can detect shifts in cabin pressure, sounds, or movement that hint at underlying issues. Reports began surfacing internally, noting that while no emergency existed, the crew's intuition told them something was different. Airlines quietly reinforced training, emphasizing careful observation and reporting, ensuring that human insight complemented the increasingly sophisticated monitoring systems on board. Airlines also had to make real-time operational adjustments. Some routes were temporarily altered to allow additional monitoring, while others required rescheduling to ensure planes underwent targeted inspections. Dispatchers and operations managers worked feverishly to balance passenger demand with precautionary measures. Every decision was scrutinized, because even a single misstep could escalate public concern or create operational chaos. The emotional impact on passengers, though largely unseen, was another layer of the story. Families boarding a Dreamliner were unaware of the invisible risk, placing their trust entirely in pilots, airlines, and regulators. Yet within the company, executives understood that the slightest leak of information could trigger panic, media scrutiny, and reputational damage. The tension between safety and perception became a high-wire act, forcing airline management to carefully navigate communication, training, and operational decisions simultaneously. Engineers worked alongside flight crews to interpret the anomaly in real-world conditions. They developed flight-specific monitoring protocols, installing temporary sensors in selected aircraft to measure stress in critical joints. Pilots were briefed to observe subtle cues during takeoff, cruising, and landing. The collaboration between human judgment and technical expertise became essential, highlighting that even the most advanced machines rely on attentive people to ensure safety. Meanwhile, internal discussions explored worst-case scenarios. If left unchecked, the hidden structural stress could worsen over time, potentially affecting flight performance or necessitating emergency maintenance. These deliberations were never made public, but they underscored the human stakes involved. The invisible threat had real implications for the lives of passengers, the careers of crew, and the trust placed in modern aviation systems. Families, passengers, and crews had unknowingly become participants in a delicate experiment where the silent growth of a flaw intersected with human vigilance. Every flight was a test of resilience, observation, and rapid response. The Dreamliner's advanced technology, which promised efficiency and comfort, also relied on the subtle coordination of human perception and engineering insight to mitigate risk. The narrative began to shift. The story was no longer just about machines or hidden flaws. It was about how people reacted, adapted, and persevered in the face of uncertainty. It was about trust, skill, and the quiet pressure of responsibility thousands of feet above the ground. Human intuition became the final line of defense, complementing technology in a partnership that was both fragile and essential. Could the human element ultimately be the key to catching what machines alone could not detect? Join us as the secrets grow even darker. The hidden weak point in the Dreamliner's architecture. The first rays of morning revealed a new layer of complexity in the Dreamliner's construction. Engineers huddled over blueprints and 3D scans, tracing the aircraft's intricate lattice of carbon fiber composites. At first glance, the plane's structure was a marvel of modern engineering, a network of overlapping panels and reinforced joints that promised strength with minimal weight. Yet the very sophistication that made it exceptional also concealed the subtle weakness now under scrutiny. One particular joint drew attention immediately. It connected multiple fuselage sections with a layered interface, blending aluminum, titanium, and carbon fiber. Designed to absorb stress and maintain rigidity during flight, it also created microscopic cavities between layers. Over time, these cavities could allow vibrations or minute impacts to accumulate unseen. Experts realized that even a tiny flaw at this junction could silently propagate, undermining a critical section of the aircraft's skeleton. Unlike traditional metal airframes, the 787's layered composites masked many structural irregularities. Engineers discovered that hidden stress fractures could remain invisible to standard inspection tools. What looked smooth from the outside could conceal a network of micro-cracks within. Each composite layer carried unique tension and fatigue properties, meaning that a defect in one layer could go unnoticed until it interacted with another. This wasn't a theoretical concern. The vibration discovered overnight suggested just such an interaction was occurring. Engineers began reconstructing the assembly sequence for the affected section. They realized that the joint in question had been installed under conditions slightly different from other planes. Humidity, curing times, and even minor variations in temperature during the bonding process could subtly alter the alignment of layers. A flaw that might seem insignificant at the factory could later amplify in flight, making detection nearly impossible with conventional maintenance procedures. Advanced scanning techniques revealed tiny gaps where adhesives had underperformed and bonding layers had compressed unevenly. The imperfections were microscopic, but in an aircraft designed to endure thousands of pressurization cycles, they could eventually compromise structural integrity. Experts noted that this area of the fuselage had rarely been scanned during routine maintenance, partly because its design concealed critical surfaces, and partly because existing protocols assumed the materials were impervious. The hidden weakness was not isolated to one aircraft. Engineers cross-referenced manufacturing records and found that several Dreamliners shared the same build characteristics. While there were no reported incidents, the potential for stress accumulation was clear. The plane's design was revolutionary, but the hidden geometry of its joints made every Dreamliner vulnerable to the same silent problem. As the team delved deeper, attention shifted to the plane's interior supports. Carbon fiber frames, once praised for weight reduction, now appeared to create stress points where layers met at unusual angles. These intersections formed channels where vibrations could amplify. Over time, these micro-movements might interact with other minor flaws, creating a domino effect that no single test had ever anticipated. The very materials that define the Dreamliner's innovation also concealed the kind of threat that can only be understood after careful, persistent analysis. Senior engineers convened to discuss possible inspection strategies. Standard ultrasonic scans were insufficient. The solution required a combination of new imaging technology, targeted physical checks, and predictive modeling to anticipate how a tiny imperfection could evolve. Each discovery deepened the sense of urgency. They were chasing an invisible adversary, a weakness hidden in plain sight by one of the most advanced aircraft designs in history. While the discovery was technical, its implications were profoundly human. Airlines could unknowingly operate planes with latent structural vulnerabilities. Pilots trusted their instruments and airframes, unaware of the invisible forces at work. The revelation raised immediate questions about safety, maintenance, and the responsibility of manufacturers to anticipate flaws that technology alone could not easily detect. Could the Dreamliner's brilliance have also sown the seeds of its own hidden danger? Come with us to explore the hidden corners of the story. The race to reinvent a fix before the world notices. The discovery of the hidden flaw had triggered a silent race against time. Engineers, regulators, and airline operators now worked in unison, determined to develop a solution before the issue ever reached the public eye. The Dreamliner, a symbol of modern aviation innovation, suddenly required interventions that had never been anticipated in its original design. Every decision carried enormous weight, and every hour mattered. Within Boeing's advanced testing facilities, prototypes were subjected to a battery of new scans. The goal was to detect stress points invisible to prior inspections. Teams experimented with high-frequency imaging, laser interferometry, and 3D structural mapping. Each technology revealed previously uncharted microstrains within the aircraft's composite layers. The process was painstaking, and initial results often contradicted earlier assumptions, forcing engineers to iterate solutions faster than ever before. Redesigning a fix required collaboration on a global scale. Suppliers in Asia, Europe, and North America were contacted simultaneously, tasked with adjusting bonding techniques, recalibrating components, and producing enhanced parts capable of reinforcing the critical joints. Logistics became a challenge. Replacements had to arrive precisely when needed, often within hours, to minimize downtime for planes already in service. No detail could be overlooked, as even a minor misalignment would compromise the entire corrective process. Engineers also developed emergency repair kits that could be applied in the field. These kits combined lightweight reinforcement brackets, precision adhesives, and specially designed sensors to monitor the joint after repair. Crews received rigorous training on installation procedures, ensuring that even technicians in remote locations could perform the repair without error. The speed and accuracy of implementation were as critical as the engineering itself. Testing became an unrelenting cycle. Each repaired joint was subjected to vibration, pressure, and load simulations far beyond normal operating conditions. Flight simulators recreated every scenario imaginable, from turbulence over the Atlantic to repeated takeoffs and landings in extreme climates. Data flowed in real time, allowing engineers to adapt their designs on the spot. The race was not against competitors or deadlines. It was against the invisible forces that could compromise the aircraft itself. Every anomaly detected, no matter how small, prompted immediate adjustments, ensuring that no potential weakness was left unexamined. Meanwhile, airline operations teams coordinated global inspections. Planes in service were systematically scheduled for evaluation, often during overnight maintenance windows. Pilots and ground crews were briefed with unprecedented detail, yet the wider public remained unaware of the magnitude of the effort. Safety and discretion were intertwined, demanding flawless execution at every level. Coordination between engineers, airlines, and maintenance crews became a delicate orchestration, leaving no room for error and highlighting the immense human effort required to safeguard every flight. After weeks of intense development, testing, and global coordination, a reliable solution emerged. Reinforced joints, recalibrated bonding procedures, and enhanced monitoring systems created a multi-layered safeguard. The combination of engineering ingenuity, operational precision, and human vigilance ensured that the flaw would no longer pose a threat. By the time the program concluded, the Dreamliner had not only been corrected, but significantly improved. Every reinforced joint, recalibrated component, and advanced monitoring system became a testament to the relentless dedication of engineers and technicians who worked around the clock. The invisible weakness that once threatened to compromise flights evolved into a symbol of proactive problem-solving, innovation, and the critical interplay between human expertise and cutting-edge technology. Aviation survived, as it always had, on constant vigilance, meticulous analysis, and the quiet determination of those who refused to let unseen risks go unchecked. The Dreamliner now flew with renewed confidence, a striking reminder that even the most advanced aircraft can conceal the oldest kinds of danger, yet with focus, collaboration, and ingenuity, These threats can be uncovered, addressed, and ultimately overcome, ensuring safety and trust for passengers and crew alike. Were you shocked by the hidden fault discovered inside the KLM Boeing 787 and the potential risks it posed to modern aviation? Share with us which detail left you the most stunned.